Okay, we're going to move on to isovolumetric processes. Let's share the screen. We'll get the PowerPoint up. There it is. All right. An isovolumetric process, sometimes called an isochoric process, proceeds at constant volume corresponding to vertical lines on a PV diagram. If the volume doesn't change, no work is done on or by the system. So W equals 0, and the first law of thermodynamics can be written as shown. This result tells us that in an isovolumetric process, the change in internal energy of a system equals the energy transferred to the system by heat. The energy transferred by heat in constant volume processes is given here. Q is equal to NCV delta T. Okay. Isothermal processes. During an isothermal process, the temperature of a system doesn't change. In an ideal gas, the internal energy U depends only on the temperature. So it follows that delta U equals 0 because delta T equals 0. In this case, the first law of thermodynamics gives W equals minus Q. We see that if the system is an ideal gas undergoing an isothermal process, the work done on the system is equal to the negative of the thermal energy transferred to the system. The figure illustrates this process. A cylinder filled with gas is in contact with a large energy reservoir that can exchange energy with the gas without changing its temperature. For a constant temperature ideal gas, P is as shown, where the numerator on the right-hand side is constant. Okay, isothermal processes. The PV diagram of a typical isothermal process is shown in the graph. That's the isothermal is the orange one, contrasted with an adiabatic process, the blue one. The pressure falls off more rapidly for an adiabatic expansion because thermal energy can't be transferred into the system. In an isothermal expansion, the system loses energy by doing work on the environment, but regains an equal amount of energy across the boundary. The work done on the environment during an isothermal process is shown here. The symbol Ln is an abbreviation for the natural logarithm. The work W done on the gas is just the negative of WENV, the work done on the environment. All right. When a process follows none of the four given models, it is possible to use the first law to get information about it. The work can be computed from the area under the curve of the PV diagram, and if the temperature at the endpoints can be found, delta U can be calculated. It's easy to get confused with ideal gas problems, so the table here shows the basic information and formulas you will need for isobaric, adiabatic, isovolumetric, isothermal, and general. All right, we'll stop right there. And the next, we're going to talk about heat engines and the second law of thermodynamics. Let's stop the share.